You know that feeling?
Yeah.
When you're trying to get your head around something really complex, like how these AI neural networks actually learn things, and you just kind of hit a wall.
Yeah, it feels like looking into a black box sometimes.
Totally. You see these amazing results, but the how and the why, it's just, well, opaque. And I always wonder, maybe you do too, are these systems really learning useful stuff? Or are they just getting super good at, memorizing the specific data we feed them?
Mm.
Like, how do we stop them from just overfitting every single training example?
That's a huge question. It's really been a core challenge in machine learning for ages, this whole idea of generalization. How do you build models that work on new stuff, not just the stuff they've seen, especially if you don't have like mountains of data?
Right.
So today, we're actually going to dig into something quite old, relatively speaking, a really important paper from 1993 that tackled exactly this problem.
1993. Wow, okay. In tech years, that's practically dinosaur territory, isn't it?
Yeah.
So what did these early pioneers figure out?
Well, the paper's by Jeffrey Hinton and Drew Van Camp. It's called Keeping Neural Networks Simple by Minimizing the Description Length of the Weights.
Okay.
And what's wild is that even though AI has changed so much since then, the fundamental concepts they explored about simplicity and how it helps networks generalize, they're still incredibly relevant.
Huh.
You can almost think of it as like a philosophical ancestor to a lot of modern techniques like L1 or L2 regularization. Those also try to, penalize complexity.
Keeping neural networks simple. I like the sound of that. That
Yeah.
definitely speaks to our listeners, the learners, who want to grasp things without getting totally bogged down in jargon. So, like, in simple terms, what was the main issue they were trying to fix?
Okay, imagine you're teaching a network to spot dogs in pictures, right? But you only have, say, 10 photos.
Right, not many.
A really complex, flexible network could easily just memorize those 10 photos perfectly, like down to the weird pattern on the wallpaper behind the dog.
Okay, I see the problem.
But then you show it a new dog picture, maybe outdoors, and bam, it completely fails. It didn't learn the idea of dog, it just memorized those specific images.
It overfit the training data.
Exactly. So this paper tackles how to train networks to find those useful general patterns, even with limited data. And their big idea centers on the amount of information stored in the network's weights.
The weights.
Hmm.
Those are the numbers that control how the network behaves, right?
Precisely. They dictate the connections and their strengths.
Gotcha. So our mission for this deep dive, then, is to unpack this 93 paper, figure out these core ideas about simplicity, and understand how they tried to measure this information in the weights.
That's the plan. We'll get into something called the minimum description length principle, MDL. It's a way of thinking about, like, the best model being the most concise explanation.
Okay.
And we'll explore their really cool ideas about using noisy weights, adding noise to control information, and also this thing called an adaptive prior distribution.
Noisy weights.
Yeah.
That still sounds backwards. Adding randomness helps. Okay. All right. Let's definitely dig into that. So the paper starts with overfitting, which we mentioned. Why this focus on limiting the information in the weights to fight overfitting?
Well, their main argument, which comes straight from this minimum description length, or MDL idea, is that a model that truly learns the underlying rules should have weights that are, in some sense, simple. They should be describable concisely.
Okay.
But if a model just memorizes the training data, noise and all, its weights will likely look really complex, kind of arbitrary, full of specific tweaks just for those examples. Those tweaks won't help with new data.
Right. Like a simple rule is easier to apply broadly
Yeah.
than a massive list of exceptions. Makes sense.
Exactly.
So how does this MDL principle actually work? It sounds like we need a balance, right, between fitting the data we have and keeping the model itself simple.
Precisely. MDL, which was really pushed by Jorma Rasanen, says the best model minimizes a total cost. It's two parts. First, the cost of describing the model itself, how complex is it? And second, the cost of describing the data, given the model, basically. How much error does the model still make on the training data?
Okay, so for neural nets, the model description cost is about describing all those weights.
Yep. And the data misfit cost is just the training error, like how wrong its predictions are on the examples it saw.
So we want weights that are easy to describe and a network that makes few mistakes on the training set. But how do you measure the cost of describing weights? That seems abstract.
This is where it gets clever. Hinton and Van Camp framed it as a communication problem. Imagine a sender trained a network and needs to tell a receiver the exact values of all the weights.
Okay.
The shorter the message needed to send those weights accurately, the simpler the model is, according to MDL. They thought about encoding these weights based on a probability distribution, like a Gaussian, a bell curve.
Right.
Now, if that Gaussian is really spread out, big standard deviation, then any particular weight value isn't super surprising. It doesn't convey a huge amount of specific information. So counterintuitively, a wider distribution can actually lead to a shorter description length, up to a point.
Wait, hang on. So if the weights are assumed to come from a really narrow, precise distribution, then each weight value is very informative and needs a longer message to transmit.
Exactly.
But if the assumed distribution is broad, the specific value is less surprising, so the message to describe it can be shorter.
You got it. And they connected this directly to a common technique called weight decay, where you penalize large weight values during training.
Oh, right. L2 regularization is a form of that, isn't it?
It is. Their point was that weight decay is like a simple, kind of crude way of doing MDL. It implicitly assumes all weights come from the same fixed Gaussian distribution centered at 0.
Interesting. So weight decay is like MDL light. But the paper says this approach has limits, right? What were they? Is it just that it treats all weights the same?
That's a key one, yes. Standard weight decay uses the same prior assumption, the same penalty, for every single weight. But in a real network, some weights might need to be large or very precise to capture the important patterns.
Right. Not a one-size-fits-all situation.
Exactly. And they also pointed out that just looking at the probability of a weight value isn't the whole story for description length. The precision needed matters too. A weight that only needs to be known roughly shouldn't cost as much to describe as one that needs to be known super precisely.
Okay, so a fixed Gaussian prior isn't flexible enough. Which brings us back to these noisy weights. That still sounds wild. How does adding noise make things simpler and stop overfitting?
Okay, so the core idea. Inject random noise, specifically zero mean Gaussian noise, into the weights during training.
Okay, why?
It forces the network to rely on patterns that are robust, things that aren't just quirks of the specific training examples. If a weight tries to fine-tune itself too much to capture some random detail in the training data, the added noise will kind of wash that out, making it harder to just memorize.
So the noise makes it harder to latch on the spurious details.
Exactly. And here's the really surprising part. Weights with higher variance, more noise, can actually be cheaper to communicate in the MDL framework.
Cheaper. Okay, now I'm lost again. More noise, more variability. Wouldn't you need to send more information? Like the average value and how noisy it is.
This is where the famous bits back argument comes in. It's really neat.
Okay, I'm ready. Bits back.
Imagine the sender trains the network with these noisy weights. They now have a posterior distribution for each weight, what the network learned about where the weight should likely be, including its noisiness.
Right.
To communicate, the sender picks a precise value for each weight from its posterior distribution, maybe using some random bits. Then they send that precise value to the receiver, encoding it using the simpler prior distribution they agreed on beforehand, like a wide Gaussian.
Okay, sending a precise value using a wide prior.
Yeah.
That sounds like it would take a lot of bits, right? Because the value could be anywhere.
Initially, yes, it seems costly. But here's the trick. The receiver gets the precise weights. They can then run the network on the training data and see how well it performs.
Okay.
Because the receiver knows the prior and sees the result, how well the precise weights fit the data, they can essentially figure out the posterior distribution the sender must have had. They can deduce the properties of the noise the sender was using. And by knowing the posterior and the precise value sent, the receiver can actually work out the random bits the sender must have used to select that precise value from the posterior distribution.
Whoa, so those random bits were communicated implicitly.
Exactly. They got communicated for free, effectively.
Yeah.
So the actual net cost isn't the initial cost of sending the precise value. It's that initial cost minus the information the receiver gained back by inferring the sender's posterior, the bits back.
Okay, my brain hurts a little, but I think I follow.
Mathematically, this net cost turns out to be the Kullback-Leibler divergence, or KL divergence, between the posterior distribution, what the network learned, and the prior distribution, what we assumed beforehand.
KL divergence. That measures how different two distributions are, right?
Spot on. So a noisier weight, higher variance in the posterior, can actually lead to a smaller KL divergence, meaning a lower communication cost, if the prior distribution also assumed a high variance. It means the learning process didn't have to change our beliefs about that weight quite as drastically.
Wow, that is genuinely counterintuitive, but really clever. So noisy weights, if the noise level is right, are actually a more efficient way to encode what's learned.
That's the core idea. But yeah, the amount of noise is critical. Too much, and the network can't learn anything useful.
Performance just tanks.
Right. Too little, and you're back to overfitting, potentially. The paper even gets into how to calculate the expected error with noisy weights, at least for simpler networks. They were really trying to make this practical.
So they needed a way to automatically tune the noisiness for each weight during training, to find that sweet spot between fitting the data and keeping the model simple.
Exactly. And they didn't stop there. They realized maybe the prior itself, that initial assumption about where weights come from, could be more flexible instead of just one Gaussian.
They used more than one.
Yeah, they explored using a mixture of several Gaussians.
A mixture. Why would that help? What's the benefit there?
Well, think about an ideal network. Maybe some weights really should be close to zero, essentially pruned away.
Huh.
But maybe other weights need to cluster around, say, +1 or -1.
Okay.
A single Gaussian centered at zero isn't great at describing that kind of structure, is it?
No, it assumes most weights want to be near zero.
But a mixture, say, one sharp Gaussian at zero and maybe two broader ones centered at +1 and -1, could capture that structure much better.
Ah, I see. So the prior becomes more complex, more adaptable.
Right. And the network can actually learn the parameters of this mixture during training, where the senders are, how wide each Gaussian is, and how important each one is, the mixing proportions. It learns the underlying statistics of the good weight values.
So it's like the network figures out different types of weights it needs and creates appropriate default distributions for them.
That's a great way to put it. And crucially, they extended the whole bits-back MDL cost calculation to work with these adaptive Gaussian mixture priors, too.
Okay, this is getting pretty sophisticated for 1993. Did they actually try this out? The paper mentioned some experiments, something about peptides.
Yeah, they did. They used the task predicting the effectiveness of peptide molecules, and importantly, they deliberately used a very small training set for a complex problem.
Setting themselves up for overfitting, basically.
Exactly. They wanted to see if their MDL method with the noisy weights and the adaptive mixture prior would shine when data was scarce. They compared it against standard weight decay.
What did they find?
They found their method achieved a lower error on the unseen test data compared to a network without noise or complexity penalty. It also showed an improvement over basic weight decay.
Promising.
Yeah, though they did note that finding the best weight decay usually needs tweaking on a separate validation set, which their method tried to avoid by adapting the complexity penalty automatically.
So even back then, they were wrestling with that fundamental bias variance trade-off, weren't they? Trying to find that balance.
Absolutely. It shows how these core challenges persist.
Okay, fascinating stuff. So even in this relatively ancient paper, we see the seeds of this ongoing quest in AI. How do we build models that learn useful things and generalize well, especially when data isn't infinite?
Definitely. And while today's deep learning uses different architectures and often way more data, these fundamental principles balancing model fit with model complexity. The idea that simpler models often generalize better, they're still super important.
Okay, let's try and wrap this up for the learner. We kicked off talking about the overfitting problem networks, just memorizing training data, especially when it's limited.
Right. And we saw how this 1993 paper brought in the minimum description length, or MDL principle, the idea that the best model isn't just the most accurate on training data, but the one that balances accuracy with simplicity, its description length.
And their way of tackling simplicity was all about the information packed into the network's weights.
Yep, which led to the really counterintuitive idea of using noisy weights, adding controlled randomness during training.
Still feels weird saying it.
Yeah, but the key insight was that this noise can actually help generalization by stopping the network from focusing on training set quirks. And amazingly, through the Bix-back logic, these noisy weights can be described more efficiently within the MDL framework.
That bits-back idea is definitely the mind-bending part, almost like a hidden communication channel.
It's a clever perspective. And we also touched on using a more flexible that adaptive mixture of Gaussians, letting the network learn the statistical patterns of good weight values itself.
Right, and the early results on that peptide problem suggested this whole approach had real potential, especially when data was scarce.
Exactly. A nice demonstration of the concepts.
Okay, so final thought then. We're now in this era of massive deep learning models, often trained on huge data sets. How relevant are these, almost philosophical ideas from 1993 about simplicity and information cost? Do MDL and efficient representation still have something to teach us?
That is the question, isn't it? I mean, think about it. Even with tons of data, overfitting is still a risk with today's incredibly complex models. And we're increasingly demanding AI that's not just accurate, but also understandable, robust, trustworthy.
Wait, not just black boxes.
Exactly. So this fundamental idea of learning efficient representations, simple, concise ways to capture the essence of the data, feels more important than ever. Maybe revisiting these early ideas about description length, about quantifying information in weights, could spark new ways to build AI that generalizes better and is less, well, opaque. So maybe something for you listening to think about. As AI becomes more embedded in our lives, where do you see that tension playing out, that trade-off between a model being complex enough to do the job versus being simple enough to trust and understand? Could these older principles still hold the key to building better AI tomorrow?